Hello there, and welcome back. What we're going to do in this video is determine the area under a curve, or should I say the value of a definite integral. In this case, it is the area under the curve because our function is non-negative. But we're going to find that area using a Riemann sum and taking the limit as the number of rectangles approaches infinity. So over to the left, we have the function f of x equals x squared plus 2 on the interval 1 to 3. And you see there we have the region is sketched there, and I do have a rectangle there that is representative of all the other rectangles. We're going to use right-hand endpoints because it turns out that getting the values of ck is easier with right-hand endpoints. So the pieces we need are the width of each rectangle, which is the width of the interval divided by the number of rectangles, which is b minus a over n. That's right here. So delta x is 3 minus 1 over n, which is 2 over n. So that's a familiar quantity that's going to be used. And then the values of our c sub k's is 1, the left-hand endpoint, plus k times delta x, which simplifies to 1 plus 2k over n. So coming over to the right, the value of the definite integral is the limit as n approaches infinity of f of ck times delta x, which is right there, the first line. So now we're going to substitute everything that we know. We have the limit as n approaches infinity of the sum of f of 1 plus 2k over n, that was the value of ck, times 2 over n. And just to note that this is all under the summation, just to avoid confusion there. So then from here, we substitute into the function, we simplify, and then we use summation formulas where possible to simplify the sum and to hopefully be able to take the limit as n goes to infinity. So here we go. So since f of x is x squared plus 2, that means we have 1 plus 2k over n squared plus 2, and then we have the times 2 over n. So then we just simplify. Squaring 1 plus 2k over n, we have these three terms, and then the plus 2, still all multiplied by 2 over n. In the next step, all we're doing is combining the like terms. The 1 plus 2 becomes the 3, so that's the only major highlight happening there. And still that whole sum multiplied by 2 over n. And then now distributing the 2 over n through, so 3 times 2 over n becomes 6 over n, and so on and so on. So now you notice we have these sums with k squared. Now k is the index of summation, so we're going to be able to utilize these summation formulas by another property of sums, which says I can now have 3 separate sums since I have a sum of a sum. A lot of sums going on there. So it's the sum, k going from 1 to infinity, of 6 over n. The 8 over n squared is a constant, so it can come outside the sum, like so. And the 8 over n to the third can be factored outside of the sum as well. So from here, this is where the summation formulas kick in. So this is equivalent to the limit as n approaches infinity. Now, the summation of 6 over n is the summation of a constant, so that means that that's equal to 6 over n times n terms, plus 8 over n squared, the summation of k starting from 1 and going to n is n times n plus 1 over 2, and the summation of k squared is k times k plus 1 times, oh, I'm sorry, not k, n, fix those there. So we have n plus 1, 2n plus 1, all over 6. So now we should be able to take the limit as n approaches infinity of that. Now let's clean some things up here. So we have the limit as n approaches infinity. 6 over n times n is 6. In the second term, we have, so if I multiply the numerator through, that's going to be 8n squared plus 8n, and that's all over 2 4n squared. And then here in the last term, we have a denominator of 6n to the third. And if we were to multiply the numerator through, well, let's see. This part right here is 2n to the third plus 3n squared plus n. So if I multiply that by 8, we have 16n to the third plus 24n squared plus 8n. Okay, and now what I'm going to do in this last step before evaluating the limit is I have the limit as n approaches infinity. We have 6 plus, now if I divide through by n squared, that's 4 plus 4 over n. And if we divide through by 6n to the third, 16 over 6 is 8 over 3. 24n squared over 6n to the third is 4 over n. And 8n over 6n to the third is 4 over 3n squared. So then as n goes to infinity, anything that has an n in the denominator is going to cancel out and go to 0. So this term goes to 0, this term goes to 0, and this term goes to 0. So we're left with 6 plus 4 plus 8 over 3, which becomes 6 plus 4 is 10. 10 is 30 over 3. So that means that the value of the definite integral is 38 over 3. And we know that a function is integrable as long as any limit that we do of this form, if we use left-hand endpoints, midpoints, random points in each of the subintervals, if we use those, it should come out to be the same sum, and it would. If we were to use left-hand endpoints, we would get 38 thirds. If we were to use midpoints, we would also get 38 thirds. So the value of the definite integral is 38 thirds.